This is our final video in this video lesson series on reaction mechanism and catalyst. So we were looking at the fact that a catalyst lowers your activation energy. And what I was saying on the last video is that if you look at where the reactants begin and where the products end up, when you add your catalyst, it does not alter your enthalpy. So remember, the enthalpy is the difference in where the reactants and the products, the difference in their overall net energy here. This is your enthalpy. And for this one, since the energy of the products is higher than the energy of the reactants, this is an endothermic reaction. But notice that all that was altered by the catalyst was the activation energy is lower here. This would be the activation energy without the catalyst. Notice it lowers the activation energy when you add your catalyst. So catalysts increase the number of collisions that are effective collisions. They increase the number of effective collisions. So if you look at these two graphs here, with your uncatalyzed reaction, this is the number of effective collisions. Notice how they're fewer. Whereas if you compare it to the catalyzed reaction, notice there's a much larger area under the graph here. You have more particles that have effective collisions. Therefore, their products can form. The last formula we want to look at is called the Arrhenius equation, and we use this equation to help us calculate a rate constant, and we can also calculate the activation energy. Now, K is your rate constant at a given temperature. A represents a frequency factor, and the E sub A represents the activation energy. R is your ideal gas law constant. And since we're talking about energy here, remember when we're dealing with energy, we use the constant that has joule per Kelvin mole for the unit. So we're using the 8.3145 value for that. Now, the Arrhenius equation rearranged looks like this. The natural log of K2 divided by K1 equals the activation energy divided by the R times 1 over T1 minus 1 over T2. Now the capital T's mean temperature. And the temperature does have to be in Kelvin. These K's are your rate constants for two different reactions. So you would be getting the data off of a data set from experimental data. So these are your rate constants. R is the 8.3145 joule per Kelvin mole. And E is your activation energy, which is in joules. Now, in class, we are going to work on these this particular example. We will be using the equation from the last slide. So if you're missing class, you want to try this one on your own. Plug it in. Make sure that you convert your temperatures to Kelvin. You must use Kelvin temperatures, and we're always going to use first and last so that our answers always match. Use first and last for your data, for your numbers to plug into the formula. So the most common mistakes is forgetting to convert your temperature to Kelvin, so don't forget to do that. Use first and last for your K's. So this would be like your K1. This will be what we use for K2. We'll use this Kelvin temperature for T1 and this Kelvin temperature for T2. You're going to plug in and solve for the activation energy. All right, so we're going to work on these in class tomorrow. And again, if you're missing class, please come see me if you have any trouble with this. There are two examples for you to try. All right. Compare